Hi, I'm Nikita. I'm a Google Cloud Developer Advocate.
And I'm Vaibhav. I'm an outbound product manager for Cloud TPUs. And today we are going to cover the core concepts you will need to know to bring distributed training to your machine learning workflows.
We'll start with an overview of different distributed training algorithms and then show you a framework for training models with billions of parameters. Before we get into the details, it's important to understand why we need distributed training in the first place. Deep learning works in part because of large datasets and large models. Using the right distributed training configuration can dramatically impact model performance, and a shorter training time makes for faster iteration to reach your modeling goals. There are two broad categories of distributed training algorithms: data parallelism and model parallelism. You can think of data parallelism as improving the efficiency of training models with massive datasets, and model parallelism as training models that are so large they don't fit in the memory of a single accelerator chip. We'll talk about both of these categories today, but let's start with data parallelism, which is generally the easier of the two to implement. One way to understand data parallelism is by thinking about the batch size. On each step of our model training, a batch of data is used to calculate gradients, which are used to update the model's weights. Generally, the larger the batch size, the more accurate the gradients are. But we can only make the batch size so large before we start to run out of GPU memory. But if we could add an additional GPU, we could double the batch size. By adding more accelerators, our model will see more data on each training step, which means that it will take less time to finish an epoch. To make this concept more concrete, let's assume our model is a linear model, y equals wx plus b. We can think of this linear model in terms of its computational graph. The matmul, or matrix multiplication operation, takes an x, the batch of training data, and w, the weights. The result of this operation is passed to the add operation with b, which is the model's bias terms. And the result of this operation is ypred, which is the model's predictions. We want a way of executing this computation such that we can leverage multiple workers. Workers in this case could be multiple accelerators, such as GPUs or TPUs on a single machine, or multiple machines, each with potentially multiple accelerators. So let's say that we have two GPUs we want to make use of. One way we might go about this is with data parallelism, where we distribute our dataset such that each worker processes a different portion of the input batch on each training step with the same model. You can see an example in the diagram on the right. The batch of data X is split in half. One slice is sent to GPU 0 and the other to GPU 1. In this case, each GPU calculates the same operations, the matmul and addition, but on different slices of the data. This means that on every step of our model training, each GPU performs the forward pass on a different slice of the input data to compute the loss. Each GPU then computes the gradients based on the loss function. But we now have two sets of gradients, one computed by GPU 0, the other by GPU 1. So we need some way of turning these two sets of gradients into one. We're going to do this by averaging the gradients in a process known as allreduce, and then use this average value to update our model parameters. Turning these two sets of gradients into one set of gradients happens at the end of each step. When implementing this type of data parallelism, you might do some pipelining to overlap the computations for efficiency, but the key takeaway here is that compared to regular non-distributed model training, where we take multiple steps through the data, in this type of data parallel training, we have an additional computation at the end of each step, which is where all of the workers communicate with each other to exchange gradients to calculate an average. Now, data parallelism can help us to more efficiently train models with large data sets. But what do you do when your model parameters start to number in the billions, or when you don't just have a large data set, but every sample in your data set is so large that you can only fit a batch size of 1 or 2 on each accelerator? Well, this is precisely where model parallelism shines. Now, you might be wondering, why on earth would I need to train a model that large? We talk a lot about how large data sets are important in deep learning, but for many language tasks, the amount of compute is also incredibly important. The image on the right is from an OpenAI paper that studied how language modeling performance improves as the model size, dataset size, and amount of compute used for training all increase. They found that within reasonable limits, these three factors were much more impactful on model performance compared to architectural hyperparameters such as network depth and width. And you might have seen this schematic from the ML Pathways talk by Jeff Dean, where he spoke about really large but sparsely activated multitask models, where only a small portion of the model is active while performing a certain task. As a result, this class of models is too large to fit on a single device. To put it simply, large models matter. So when we have a model that's too large to fit on a single device, how do we go about splitting it up? Here's an overview of different model parallelism approaches. A key difference in these approaches is the sharding or partitioning, which just refers to how you choose to slice the model. You can think about sharding your model layer by layer, which is known as pipeline parallel. For example, here's a model with 4 layers. You can see in the image on the right that we can partition our model across 4 devices, such that different layers of our model are on each device. Layer 1 on device 1, layer 2 on device 2, etc. Alternatively, you could split across parameters and activations within layers, which is known as tensor parallel. Here's the same model from before, but with the tensor parallel strategy, where each layer in our model is partitioned across the devices. So for layer 1, some of the parameters are on device 1, some are on device 2, some are on device 3, etc. Now that you've seen the underlying theory and concepts, I'll hand it over to Vaibhav, who will walk through some examples of pipeline and tensor parallelism approaches from Google Research, and then show you how you can start experimenting with model parallelism today.
Thank you, Nikita. And hello, everyone. Now we will start with some concrete examples of pipeline parallelism, specifically the type called synchronous update pipeline parallelism. Then we'll briefly review the tensor parallel approaches, that is spatial and parameter partitioning. Finally, we'll motivate GSPMD, what it is, why should you care, and how you can use it. Note that you can express pipeline parallel architectures as well with GSPMD. And why are we reviewing these different approaches? It is because in practice, your real architectures may be a combination of 2 or more of these approaches, so it will be helpful to get familiar with them. Now let's take a quick peek into an example of pipeline parallelism. Recall that in pipeline parallelism, we partition our model layer-wise across multiple devices or workers. Here we're looking at gpipe, which used microbatching. That's time slice the mini batches per worker and further pipeline these micro batches through these workers. This means while one stage of the pipeline is working on a micro batch, the preceding stage is working on the next micro batch, as shown in the diagram on the right. This pipelining follows in the reverse order during backward pass. In comparison to pipelining without micro batches, this approach helps to reduce the pipeline bubble. Notice also the update on all the workers stacked at the end after the last backward pass, and this is why this class of architecture is called synchronous update architecture. There have been several important improvements in pipeline architectures since gpipe, among them asynchronous update-based architectures such as TeraPipe and PipeDream. Now let's talk about tensor parallel approaches, beginning with spatial partitioning. This was introduced in the Mesh TensorFlow library. An early application of this parallelism was to work with extremely large images, such as ones for diabetic retinopathy or a 3D scan. Here the input is split along X and Y dimensions across the workers. Notice that this is different from the data parallelism where the split happens across the batch dimension. Also, the downstream network is adapted such that the collection of workers still act as if the original network was working on the full image. This entails communication amongst devices, also called collective communication, in the forward and the backward, as well as during gradient synchronization. Notice also that the split was done in such a way that each worker is executing an identical computation and communication graph. This idea is the foundation of a more generic framework to achieve such partitioning, later called GSPMD, or Generalized Single Program Multiple Data Approach, orchestrated by XLA Compiler. We'll take a more detailed look into GSPMD and reasons why it's helpful and how to use it in the remainder of this talk. Now, let's develop some further intuition about SPMD, beginning with parameter partitioning for a simple two-layer model. Here's our two-layer model as we would see in a data parallel setting. X is the input, W1 and W2 are weights corresponding to the two layers. And here's the forward pass computation graph of this model. There is a corresponding backward computation graph as well, not shown here for brevity. Communication happens when the gradient synchronization is done, that is, after the backward pass. Let's see what happens when we do tensor parallel partitioning or parameter partitioning of this model across two devices. Now, before we go into details, here is the takeaway. Even a two-layer model partitioned across two workers introduces a significant amount of communication steps in the forward and the backward pass. Now let's see how this happens. In this example, we have sharded X into two column-wise parts. The W1 and W2 parameters are partitioned row-wise and column-wise respectively. The dotted lines in the diagram show these different partitions across two workers. Let's look at the computation graph. Notice that we are showing the partition graph here. That is, each worker has the same graph working with the respective part of all these matrices. Single program, multiple data. In the forward pass, we begin with an all-gather operation on X, shown by yellow bubble, which means we collect partitions of X from the two workers. The rest of the forward pass is the same, except before generating the output, we do a reduce scatter operation, which means that we average the corresponding shards of Y on respective workers. Let it sink for a moment. Simply put, when the forward pass is finished, each device or worker will have the reduced or averaged version corresponding to the shard that it is holding. You can think of all gather and reduce scatter as conjugates of each other. One in the forward pass means the other in the backward pass. Hence, in the backward pass, we see these conjugates in the reverse order. Once the forward and backward pass are done, the gradient synchronization will require its own communication as needed. If it was too many details to register, just remember, the takeaway is even a simple model partitioning across two workers introduces a significant communication steps in forward and backward pass. Imagine a much larger model with scores if not hundreds of layers, and you will notice that the ratio of compute and communicate is what determines how efficient is the distributed training. That is, how efficiently we are using the accelerators. There are three key factors which will determine how well your parameter partitioning will work. As you may have already guessed, the choice of sharding configuration, number 1, activation memory trade-off with compute, number 2, and compute and communication overlap, number 3. And you will experiment with these three factors to arrive at an efficient distributed training. Let's review these factors one by one. First is the choice of sharding or partitioning configuration. One concept to register here is, in any real-life model parallel design, you would want to experiment with multiple sharding configuration. Let's see why. The drawing here is from the Mesh TensorFlow paper published in 2018. The authors established a powerful insight from the simple example of C is equal to A into B matrix operation. If we view this computation as an iteration space of indices I, K, and J, it has this cuboid shape, and it can be partitioned in the following three ways along 1 dimension, 2 dimensions, or 3 dimensions. The authors show that computation corresponds to the volume of the slices on each worker, and communication corresponds to the surface area. And the insight was that the fully sharded configuration had the best compute to communication ratio. And once again, apply this to more complex, large multi-layer setup. The takeaway here is sharding configuration matters. And you want to be able to iterate over multiple configurations before you find the optimal one. Now to factor number 2, activation memory trade-off, which is in fact not unique to model parallel training, but becomes more important for larger models. First, a little deep learning 101. Why are we talking about saving activations? Aren't they computed in the forward pass? True. Let's take a look at this small graph. Here, H is the activation from the previous layer. W is the weight of this layer, and W transpose H is going to the ReLU activation. Now let's follow the backward pass. We notice that the gradient of W requires H, that is the activation value. And now we see why activation is needed in the backward pass. And in the simplest setup, these activations are just stored in the accelerator memory. In case of large models, since we are memory constrained, we look for options to reduce the accelerator memory usage. And we do this by making some trade-offs. This diagram shows these trade-offs. If we decide to offload activations to the host memory, we trade off with host to device read time penalty. If instead we choose to recompute activation during backward pass, we trade off compute cycles. Since activation volume is intimately related to the sharding configuration, this trade-off is also iterative. That is, you will need to experiment with different extent of save, remat, or offload. The third factor for efficiency is the possibility of overlapping compute and communication. For example, if all gather and matrix multiplication can be overlapped. And this certainly can be engineered, but what if such optimization could be done automatically for you by your framework? The good news is that it is possible. There exists such a framework which can not only do these optimizations, but also allow you to easily iterate over sharding configurations and different activation memory trade-offs you would want. And this is using GSPMD. GSPMD was introduced in 2021 paper from Google Research. XLA-SPMD partitioner in this work allows you to express your tensor parallel and pipeline parallel architectures. You define your device mesh configuration and then specify sharding annotations for the full model, providing hints on how some of the key tensors should be distributed across the device mesh. The partitioner is then able to propagate the sharding configuration throughout the graph and create a partition graph which look identical in shape but work with different partitions of data, weight, and activation tensors, and hence the name single program or single graph and multiple data. Now let's look at an example with a two-layer model and CSPMD in action on Google Cloud TPUs. XLA-SPMD with two-layer network. In this notebook, the computation environment is Cloud TPU VM v38 instance. Instruction for creating this instance can be found at the official documentation page for Cloud TPU, the quick start page. Once you have created the Cloud TPU VM instance, you can SSH into it using this command. Notice the SSH flag for port forwarding your localhost 9009 to the 9009 port of your TPU VM. Once you have SSH into your TPU VM, you can then start your Jupyter Notebook service at port 9009, and then you can access this at localhost :909 from your own browser. Once your Jupyter service is running in your browser, you can then upload this notebook and start your experimentation. In the first part, we show the training without any partitioning. So here we import basic libraries, we do some sanity check to make sure all the devices are detected. We define the two-layer network and then define functions to express the initialization of the model and optimizer. Then we define the loss function and the update step function for the training. And finally, using these functions, we do the initialization and run the training updates for 10 steps in this case, and print out the training loss. Now let's see how these steps change in case of partitioned model. Here we begin by defining the mesh specification or the device mesh, which is required by XLA SPMD partitioner. We express the device array, which we also listed in the beginning as a sanity check, into this two-dimensional logical array, and we name these two dimensions as D and M, or it could be named data and model, or whatever name you prefer. And then XLA SPMD comes into play when we define the PGIT transformed version of the different functions that we defined above for facilitating training. For example, in this case, we are defining the partitioned version of the model initialization function. And where XLA SPMD comes into play is that it uses the sharding annotation or partitioning specification for inputs and outputs and uses these to propagate these annotations throughout the function and finally create a partitioned version of the function computation graph that can then be executed across the specified device array. Notice that the partitioning spec is defined in terms of the named axis of the device mesh. We define these partition version for optimizer initialization as well as the update step functions, and finally use these partition definitions instead of the usual function definitions to express the same training loop that we wrote in the first part of this notebook. And we notice that it is able to yield the same training loss that we saw in the earlier example. To take a more sizable example, let's look at T5. In terms of model architecture, T5 is similar to the original transformer architecture with some differences which we'll not discuss here. T5 is an encoder-decoder-based unified text-to-text framework for tasks such as translation, question answering, and classification. And T5X is the JAX implementation of T5. It provides a generalized framework for expressing large transformer-based models, encoder-decoder, encoder-only, or decoder-only variants, and provides a training framework to train these models with TF data pipelines using XLA SPMD on TPUs. This diagram shows the basic encoder-decoder building block, which is stacked to express multiple architecture. And the code snippet shows how these architectures can be expressed as config, defining some of the architectural parameters. Notice also the remat policy in the config that points to the remat trade-off we discussed earlier. Now we define the device mesh. The snippet on the right defines the grouping of TPU chips or cores along two named axes, in this case called model or data. And next, we define a partition config that specifies the model parallel size as well as the mapping of logical axes used inside the model to named mesh axes defined in the previous step. Here the vocab, MLP, embed are the named internal axes which are mapped to the mesh axis. And finally, here is an example of adding sharding annotations in your model code which can be propagated by XLA SPMD partitioner. And that's it. In summary, T5X shows an SPMD-based framework that allows you to easily experiment with multiple sharding configs, experiment with various degrees of activation, rematerialization trade-offs, allows you to take advantage of compute communication overlap brought to you by XLA compiler. And here are some of the results from the experiments using Excel SPMD on various device and model configurations. On the y-axis, we show the measured and the effective floating point operations, or flops, achieved expressed as utilizations of hardware peak flops. Measured and effective utilization differ because additional multiplication done for activation rematerialization is not useful. Therefore, effective flops should be considered while measuring the efficiency of the hardware. On the x-axis, we show various TPU-v4 cluster sizes expressed in number of chips. The strong scaling graph shows the performance when we train the same size of workload across various cluster sizes. And the weak scaling shows the performance when we scale the work along with the cluster sizes. High utilization numbers are better, and we want utilization to stay flat or improve as we scale. We hope that this introduction was helpful to ignite your interest in model parallel training in general and SPMD in particular. You can start experimenting with example provided in the notebook or some of these open source examples from Google Research and other research teams across the world. Thank you.